So the conclusion of the exciting adventures of 1.8, inequalities, specifically in this case, nonlinear. The reason why I sort of separated nonlinear from linear is that, well, it was my hope that yesterday's practice was sort of pretty straightforward and easy because the idea was solving a linear inequality, 99% the same as solving a linear equation. Nonlinear, however, requires you to do like extra strategies. The reason being, well, as you guys can see in the agenda, our two types that we're going to look at are polynomial inequalities and rational inequalities. Well, if we equate inequalities to equations, say for instance rational equations, you don't have to write this down, I'm going to erase it later, like 1 over 2x minus 3 over 4x equals 2, you know that my technique to solve it is to clear the fraction, multiply both sides by the LCD, in this case it's 4x. Well, if I change this to an inequality, say, and I multiply by 4x, here's my problem. X is a variable. It could be anything. I don't know if x is positive or negative. And that is a problem for inequalities because if x is a negative, I have to flip the symbol. But if x is positive, I don't. Which one's right? Which one's wrong? We simply don't know as mathematicians, which is why we really can't use this strategy or this technique when it comes to nonlinear inequalities. So we're back to square one. We need new methods. We need new techniques. That strategy, if I can spell, strategy. What I prefer, this is not the only way to do these, but this is the way I'm going to approach it, is using sign diagrams. So if you came from me in Algebra 2, you know what these are, you know how much I love these. If you've never done sign diagrams before, this is what they are. So a sign diagram is sort of like you guys know, like when you are assigned a book to read in English, you know, you're supposed to read the book, but you know, there are like Spark Notes or the movies. Not that you would ever do that, of course. That's what a sign diagram is. A sign diagram is sort of like the Spark Notes versions of a graph. It gives you information about the graph without the hassle of actually sketching it out. So we are going to need some pieces of information to do a graph light, say. So to create a sign diagram, whatever inequality you have, polynomial inequality or rational inequality, the first step is the same. You want 0 on one side. Okay. So that means get all the terms onto one side. So I don't care if it's polynomial or rational, get everything onto one side. Once you get everything into one side, you pretend, yes, I know this is high-level pre-calculus, but we're going to go back to kindergarten and pretend. We pretend the problem is an equation and solve. That is to say, we ignore the inequality, we pretend it's an equal sign, and then you solve it like normal. For rationals, you're going to set the numerator, or I'll use low-tech words. You're going to set the top and the bottom equal to 0. Separately, right? So since a rational inequality technically has two parts, the numerator and denominator, whereas a polynomial only has one part, I'm just going to add the extra tidbit. You're going to pretend the problem is an equal sign, but for rational equations, just set both the top and bottom separately equal to 0 and solve. You're going to plot your answers on a number line. If you can sort of like close your eyes and visualize a number line filled with points, filled with plotted points, hopefully you can visualize that that number line gets chopped up into itty-bitty pieces, into intervals. The last thing we're going to do is we're going to test numbers from each interval. Right? And in mathematics, to test something, that just means to substitute and plug it in. These are the 4 steps to create a sign diagram, and believe it or not, it will allow you to solve basically any inequality. We could do these for linear inequalities too, but it's a bit overkill. But it's the perfect level of difficulty for polynomial and rational inequalities. If you still can't picture this, what was he talking about? Intervals, testing? I think it's a lot easier to see with an example. So let's just do 2 examples, one polynomial, one rational. Hopefully you guys get the idea. And that's it. That's all the lesson is, 2 examples. Unless you guys want more. Suppose I ask you guys to solve 5x squared plus 3x is greater than or equal to 3x squared plus 2. Now, I sort of scrolled my screen up, but hopefully the notes are still in front of your face. I'm just going to follow the bullet points to the T. First bullet point, I want 0 on one side. That means bring everything over to one side. I sort of like the degree, the biggest exponent positive. So let's move everything to the left. Minus 3x squares and minus 2. 5x squared minus 3x squared is 2x squares. And a 3x minus 2, they're not like terms, so you just leave them separate. Plus 3x minus 2. So now the first bullet point is achieved. We've got 0 on one side. At this stage, we're going to play pretend. But when we play pretend, we don't want to forget the original problem. So in the back of my mind, or I guess I have a highlighter, I'm just going to remember him. We're going to basically ignore him, but not forget about him. Even though that's sort of like rude, ignoring someone but not forgetting about them. And then we're going to pretend that the problem is 2x squared plus 3x minus 2 equals 0. Solve it like normal. This is lesson 1.5. This is algebra 2, algebra 1. Go, automatic. Solve. It's a quadratic, so solve it by factoring, completing the square, quadratic formula, yada, yada, yada. This guy is factorable, so that's the easiest route to go. 2x and x, so it's going to be 2x minus 1, x plus 2. And then 0 product property, set both of them equal to 0. And then you can solve. So x equals 1/2, x equals -2. So that is the second bullet point. Pretend it's an equal sign and solve it like normal. The third bullet point is to plot this on a number line. And you don't have to draw tick marks. Do a lazy man number line. Here's a -2. Here's a 1/2. Sure, why not? And we have our first footnote. And I will not use yellow. Our first footnote. Whether or not these solutions are open or closed depends on the inequality. If it's strictly less than or greater than, it's open. If it's or equals to, it will be closed. So if you can look at the original problem, we have an or equals to, so our points will be closed. This is where it's time to go fishing, time to test. Hopefully you can see that these 2 points chop up the number line to 3 pieces, and I'm going to highlight them here, but I'm going to erase them later. The left piece, the middle piece, the right piece. All you got to do is just pick a random number into those regions and plug into the inequality. Say, I don't know, x is -3, x is 0, and 1. The question is, what do you plug it into? The idea is that you want to plug it into the inequality that you get once you have a 0 on one side. So it was at this stage here. I'm going to erase the highlight. It was at, I highlighted a whole bunch. Oops. You know what? Screw it. Forget that other two. 3. Thank you. It was at this stage here where we got the 0 on one side. So technically speaking, this is what you should be plugging into. But I always try to plug into the factored form as much as possible. So this at this line is actually where we got the factored form. So your choice. You can plug it into the loose separate terms and then just plug into your calculator or do mental math. Or you can plug into the factored form. The reason why I like the factored form is because this is a sign diagram. It's not a number diagram. It's a sign diagram. So I only care about the positives or the negatives. I don't care if it's a 12 or a 7 or a 3. I just care if it's positive or negative. So I'm going to test, bless you, x equals -3 into the factored form.
Mr. Bell?
Yes.
Wasn't it a greater than sign?
Yes, it was. Thank you. Greater than symbol. I'm still going to use this video.
Okay.
So let's plug it in. I'm only going to show the work for the first one, and then for the others, we're going to sort of use mental math because I think you get the idea. So plug in a -3, plug in a -3. And here's the thing. I don't care about the answer. I just care about plus or minus. So 2 times -3 is -6 minus 1. I don't care what the answer is. All I care about is that it's negative. The second parentheses, -3 plus 2 is negative. Negative times a negative, a positive. So I'm going to put a positive in the region that I test. And then you rinse and repeat. You guys get the idea? Yeah. So is it okay if I fast forward through the test? Yeah. Let's test x equals 0. If you're wondering, hey, whoa, you're going too fast. Where are you getting these? All I'm doing is just plugging it in and calculating. So plugging a 0 for the x, 2 times 0 minus 1 is negative. 0 plus 2 is positive. Negative times a positive is a negative. Let's test x equals 1. 2 times 1 minus 1 is positive. 1 plus 2 is positive. Positive times positive is a positive. Now, okay, that's it. This is the completed sign diagram. We did the 4 bullet points. Now it's time to actually answer the question. Answer the question here. What values of x would make this true? To do that, you have to look at the inequality that has the 0 attached to it. So all I'm going to do is look at this guy right here. We are going to look at greater than or equal to 0. We chose 0 for a reason. If you can envision a number line, 0 is right smack dab in the middle. 0 is like the neutral point. 0 is the balancing point between the positive numbers and the negative numbers. So you have to sort of use logic. Greater than 0. Those are numbers bigger than 0. Those are positive numbers. So this problem is telling you, hey, your answer is the positive sections, are the positive regions. And in our sign diagram, it's very easy to see that this part here is positive because it has the plus sign above it. And this part here is positive. That is the visual representation of our solution set. You solved it. Easy peasy? Yep. The instructions on the practice and on the upcoming tests will say put your answers in interval notation. So just take one extra step, write in interval notation. So my final answer that I will submit will be -infinity to -2 union 1/2 to infinity. That would be the answer I would accept. If you're still sketchy on interval notation, talk to me. I can come up with a whole bunch of examples for you to practice. Okie dokie? That's basically the gist of it. So if you can understand polynomial inequalities, you can solve like 90% of all the inequality problems I'll give you. The remaining 10%, or less than that, will come from this example here. What changes when I give you a denominator? Rational inequality. Not much. So with rational inequalities, repeat everything, all the logic that we did in the previous example, except you're going to add this idea. you want one solid fraction. So yes, you want to get everything onto one side. You want to set the numerator equal to 0, set the denominator equal to 0, all that fun stuff. But before you do anything, you want one solid fraction. Other than that, the steps are basically identical. So suppose I ask you to solve, and let's do a subtraction one. 3 over x minus 1 minus 4 over x is, bless you, greater than or equal to 1. Or heck, let's do less than. Let's give some negatives some love. And let's give the strictly less than inequality some love. And I'm kidding. So let's follow our steps. You want to get 0 on one side, so very obvious our first step should be to minus the 1, right? That's basically the only way we can solve these. Get a 0. So this is where the extra footnote, extra bullet point comes into play. I don't want to start solving this until I get one solid fraction. So this is, I want to say 1.3. Adding and subtracting fractions. To add and subtract fractions, you need the common denominator, which means you need the LCD. Hopefully this example is simple enough where we don't have to do anything crazy. The LCD is just both of them. Yeah. So because we're not clearing the fraction, we're not multiplying by the LCD, we are multiplying to get to the LCD. So I hope we can all see that the first fraction needs an extra x. The middle needs an x minus 1. And the last one needs both pieces. Let's remember from, I think it was 1.3 or 1.4, when I personally do rational expressions, I do not multiply out the denominator, so I'll leave it in factored form. The denominators are all the same now, so I can just write it as one giant fraction. And then just work the tops. 3 times x is 3x. Please be careful with the subtraction. I know someone's going to make a mistake. Someone's going to lose points for it, but I'll say it anyway. When you're doing rational expressions and you have a subtraction, you must distribute that negative. So this is negative 4 times x is negative 4x. And this is negative 4 times a minus 1 is a positive 4. Same thing on the other side. Distribute this negative when you do x times x minus 1, which will give you negative x squared plus x. Let's simplify. Let's combine like terms. Oh, that's neat. All the x's are gone, so you're left with 4 minus x squares over x minus 1 less than 0. So we've accomplished our goal. We have 0 on one side, and we have one solid fraction. There's no extra pluses or minuses on the outside. So now it's time to pretend. So I'm going to not forget about him. I'm going to remember him, but I'm going to set separately the top equal to 0, and separately set the bottom equal to 0. And then just solve like normal. The left equation, you guys see they're perfect squares, difference of perfect squares, factorable. Geez, that's just for whoever made this example, wanted it to work. Oh, plus. So x equals 2, x equals negative 2. And this guy here is x equals 0 and x equals 1. All right. Sign diagram time. Plot your numbers. Negative 2, 0, 1, 2. We've already done a footnote on how to determine if the numerator is going to be solid or full. Here's an extra footnote. Answers from the bottom equaling 0 is always open. Doesn't matter. Answers you get by setting the bottom equal to 0 will always be open because those are your excluded values. We can never ever divide by 0, so you're always leaving them out. But it's sort of a moot point because look at the original inequality. There's no or equals to part. There's no line, so they're all open anyway. So let's test. Let's see. Test x equals -3. Say x equals -1. If you ever have to test between two consecutive integers, just use a fraction or a decimal. Between 0 and 1, 1/2. Between 1 and 2, 1.5, say. And then 3. What am I testing into? We are testing into the saved inequality. So we are testing into, bless you, 4 minus x squared over x minus 1. But you know what I said before. I always like to test it in factored form whenever possible because it's easier to tell pluses or minuses. And we've already saw that the numerator is factorable. So I'm actually going to test it in this guy. Everyone understand how to test? Yeah. Can I fast forward through the testing? Stop me anytime if my mental math is too fast, but all I'm literally doing is plugging in every single one of those blue numbers in for x's. So let's test x equals -3. In the first parentheses, 2 minus -3 is positive. 2 plus -3 is negative. -3 by itself is negative. -3 minus 1 is negative. Positive times a negative over negative times a negative gives me a final answer of negative. And then just rinse and repeat. Let's do -1. So 2 minus a -1 is a positive. 2 plus -1 is a positive. -1 by itself is a negative. -1 minus 1 is a negative, which gives you a positive. Let's test 1/2. 2 minus a half is positive. 2 plus a half is a positive. 1/2 by itself is positive. 1/2 minus 1, unfortunately, is a negative. Ruining the whole thing. The whole thing is negative. Let's test 1.5. 2 minus 1.5 is positive. 2 plus 1.5 is positive. 1.5 by itself is positive. 1.5 minus 1 is positive. Positive, positive, positive all the way around. And testing x equals 3, we can probably hazard a guess. It's going to give us a negative, right? I got lazy. I skipped that one. But it's negative. Now, those astute people, those guys who got like A stars on, recognizing patterns in kindergarten, can probably say, gee, Mr. Vo, I recognize something going on here. It's just flip-flops, negative, positive, negative, positive, negative, positive. Does that always happen? And you would want me to say yes. Unfortunately, the answer is no. So, yes, does it happen more often than it doesn't? Perhaps, but you cannot be 100% sure. So, yeah, please go through the tests. Seems like it's a lot of work, but it's really quick mental math. You have to test it out. It will not always be this nice pattern. So we got to fill in our answer. Our original inequality was less than 0, positive or negative. What type of numbers are less than 0? Negative numbers. So you're shading the negative regions. So that is your answer. You start at negative infinity, go all the way to -2. Union, start at 0, go all the way to 1. Union, start at 2, go all the way to infinity. That is your answer. Sign diagrams. They are, to me, they're fun. It's sort of like drawing without needing to be an artist. So to solve inequalities, nonlinear inequalities, get everything onto one side, factor as much as possible, solve it as if it was an equal sign, and make your sign diagram. That is the completion of 1.8.